Chapter 8: X-rays. So the discovery of cathode rays had just opened a new chapter in the field of research and shifted science to a whole new level. We know that cathode rays are no more than just a beam of electrons accelerated in a vacuum from a cathode to an anode. This is the sort of thing that fascinated the scientists of the day, and as they experimented further, this led not just to the discovery of the electron, but also the discovery of X-rays. X-rays were discovered by Wilhelm Conrad Röntgen in 1895. He had photographic plates which were kept in a light-tight container so that no light could get to these plates. These were kept in a drawer. For some reason, Röntgen decided to develop the plates after having played with his cathode ray tubes. Remember that light from the tube had no way of getting to the photographic plates, yet when he developed the plates, they were exposed. There were markings that shouldn't have been there. And of course, this meant that some form of rays had exposed the plates. And because Röntgen didn't know the rays, he called them X-rays, meaning unknown. Today, we know that X-rays is an electromagnetic radiation. X-rays are produced by fast-moving electrons when they are suddenly stopped by a target material like heavy metal. So the electrons in the cathode ray tube produce X-rays when stopped suddenly by the anode. Today, X-rays are produced in an X-ray tube, which is just a cathode ray tube with few modifications. The X-ray tube consists of an evacuated discharge tube. There is a tungsten filament fused to one of the sides of the tube. The filament is coated with barium oxide to get a copious supply of electrons. The filament is heated with the help of a DC circuit. The DC circuit consists of a battery, rheostat, and an ammeter. There is a hollow molybdenum cylinder surrounding the filament. This cylinder, which is called the cylindrical shield, is maintained at a negative potential so that it focuses electrons emitted by the filament onto the anode. A tungsten block is used as the anode, and it is held at an angle of 45 degrees to the horizontal. The anode is embedded on the copper block and is connected to a copper rod. There is an arrangement to cool the copper rod. The anode and the cathode are connected to a positive and negative terminals of a high-tension supply. The filament is heated by passing a suitable current through it. The filament emits electrons. The cylindrical shield helps in focusing the electrons emitted from the filament onto a point onto the anode. The negative charge on the cylindrical shield focuses the electrons to converge at a point on the anode. The electrons strike the anode with a large amount of kinetic energy. The major part of the energy of the incident electrons gets converted into heat, and the remaining part appears in the form of X-rays. Properties of X-rays. X-rays are uncharged. Properties of X-rays. X-rays are uncharged and are therefore not deflected by a magnetic or electric field. They penetrate matter with the least penetration occurring in materials of high density like lead. X-rays affect photographic emulsions, a property used in X-ray photography. X-rays cause photoelectric emissions. They cause fluorescence in certain substances like zinc sulfide. X-rays are electromagnetic radiations of shorter wavelength than visible light. They can be plane polarized and diffracted, showing that they are waves in nature. X-rays travel in straight lines at the speed of light, 300 million meters per second. X-rays are high-energy light rays with wavelength between 3 to 0.03 nanometers, so small that some X-rays are no bigger than many individual atoms. In the electromagnetic spectrum, X-rays fall between gamma rays and the UV rays. Energy of X-rays. If a bombarding electron is stopped in a single collision, most or all of its energy is converted to X-ray energy. At a given accelerating potential difference, the X-rays produced will have varying wavelengths, with the shortest, lambda minimum, corresponding to a collision in which all the energy is assumed to have been converted to X-rays. The kinetic energy of the bombarding electron is practically equal to electron volt and is given by kinetic energy is equal to EV, where E is the electron charge and V the accelerating potential difference. When all the kinetic energy of an electron is used to produce the X-ray energy, the frequency of the X-rays will be maximum, F maximum. Using Planck's theory, the X-ray energy is given by E is equal to HF, where H is Planck's constant and F the frequency of radiation. Therefore, EV is equal to HF maximum. Since C is equal to F lambda, where C is the velocity of light, F maximum is equal to C over lambda minimum. Therefore, EV is equal to H C over lambda maximum. This shows that the most energetic X-rays have the shortest wavelength. An example. An X-ray tube has an accelerating potential difference of 100 kilovolts. What is the shortest wavelength in its X-ray beam? Solution: EV is equal to HF maximum, which is equal to H times C over lambda minimum. Lambda minimum is equal to HC over EV. If you do that, you'll get 1.24 times 10 to power negative 11 meters. Uses of X-rays. In medicine, X-rays are used in hospitals and medical research centers for diagnosis and treatment of diseases. The diagnosis involves a process called X-ray imaging, in which X-rays are allowed to cast a shadow onto a photographic plate. Examination of the photographic film reveals the injury or the infection of the tissue. A broken limb, for example, when X-rayed, will reveal the nature of the fracture on the bone. X-rays are also used in the treatment of tumors by focusing a controlled beam of X-rays onto tissues. In the laboratories, scientists fire beams of X-rays at unknown substances to learn what elements they contain and decode their atomic structure. This is how scientists unravel complex molecules like penicillin and the DNA. X-rays have security applications like airport baggage checks and also as metal detectors.